Yes. So in photochemistry, in your last class, we learn about photochemistry of alpha gamma beta unsaturated carbonyl. Complete photochemistry we learn, such as photocyclodimerization, photocyclodation, and some simple pi bond migration as well as cis trans isomerization we did. Later on, photochemistry of 4,4 disubstituted cyclohexenone. One more is cyclohexadienone. So complete mechanism I given. Then take some applications on that and predict the answer. Here I am writing methyl and here methyl. So photochemically, if they given, so what is your answer? Means can I convert this 6-membered into 5-membered or not? Then this 3-membered ring formation takes place here. This is the answer. If these two are aliphatic, your answer is 5-membered ring. It may be any kind of aliphatic. See, here it may be ethyl or ethyl, identical or non-identical, your answer remains same. 5-membered, write down 3-membered, ethyl and this is methyl. That is the answer. If it is 4,4 disubstituted cyclohexenone, if these two are aliphatic, on the time 5-membered and 3-membered ring carry 2 substitutions. So it may be identical or non-identical substitution, your answer remains same. See, here I am writing ethyl and here methyl. So photochemically irradiated. So common solvent is tertiary butyl alcohol. So on that time see, this is ethyl and this is methyl. That is the answer. Okay. So around this particular carbon, if 2 aliphatic groups are present, 2 aliphatic groups. So on that time this carbon you write down here as it is without shifting any group. Okay. Suppose if 2 aromatic rings are present, photochemically TBuOH. So on that time 5-membered ring is as it is. Now see, one ring will be migrated here, other will be over here. So always these 2 points having cis stereochemistry. You focus on these 2. If 2 are alkyl, so there is no shift of any group. Only this carbon shifted to right side. But if both are aromatic rings, on that time one ring will be shifted over here. Okay. So whichever is giving more stable, whichever is giving more stability, that is a migrating group. Suppose see, if I write a aromatic ring, and see here I am writing benzene and here I am writing benzene with cyano. So when 2 different groups are present, which is a migrating group? That migrating group is going to settle down on 3-membered ring. See, first write down 3-membered and this. So whichever is a migrating group, that will settle down on 3-membered ring. Whichever is not migrating, that is settled down on fused carbon. So whichever is giving more stability, that is a migrating group. Okay. So now phenyl is a migrating group, and here I am writing benzene with this. This is cyano, and here this is C double bond O. Suppose if alkyl aryl both are given, here I am giving methyl and here alkyl both are given. So then which is migrating group here? Which is giving more stability? Phenyl. Phenyl is migrating group. When phenyl is giving more stability, that will be a migrating group on this point. And here you may get methyl and here it is hydrogen. So that is the answer. If 2 alkyl groups are present, write down 3-membered ring. Don't write any substitution here. If both are alkyl. Suppose if both are aryl, you migrate 1 phenyl. Whichever is giving more stability, that we need to give. Means indirectly, whichever aryl ring having more electron density, that is a migrating group. See, between these two, which carry more electron density? Benzene. This benzene carry more electron density, that's why it is a migrating group. Okay, so between phenyl and methyl, which will give more stability for carbocation? Phenyl. So phenyl is a better releasing group, that's why it is a migrating group. These shortcuts you need to remember. Clear? Right. Which one? When you migrate phenyl, you will get unstable cation. Unstable cation can take proton very fastly. That is the reason. What you are saying, that is right, but thing is, see, so here two groups are present, methyl and phenyl. Now here you will get carbocation. Initially you will get this intermediate. Now what happens, see, here there is a ring formation takes place here, right? So initially you will get this one. Now whenever if it is come back, suppose if I migrate phenyl, then whether you will get unstable cation or stable cation. Unstable cation. Unstable cation having a more attraction capacity. Suppose if it is a stable cation, and if pi electrons are also stable, on that time relaxation time is required. But right now cation is unstable, it can attract this very fastly. That's why here if deficiency is very high, it can attract very fastly. Two types of cations we can generate, stable cation, unstable cation. Actually stable cation we need to generate. For which case, if reaction is very slow, on that time lifetime of cation should be increases. If reaction is very slow, lifetime of cation increases, then only it will take very slowly. But reaction is very fast. If reaction is very fast, and if you create an unstable cation, so percentage cannot increases. So that's why unstable cation, if you want to react with this, then what happens is sigma bond formation takes place very fastly. So try to generate unstable cation so that cyclation takes place very fastly. Otherwise what happens? It is slow and cation also slow. Reaction takes place much more time. One should be very fast. Either cation should be stable, otherwise anion should be unstable. Suppose if cation is unstable, anion should be stable. Any one this you need to apply. If both are stable, no reaction. Both are stable, no reaction. Both are unstable, no reaction, because both will fight with each other. And one should be stable, other should be unstable. This link every time apply for nucleophile and electrophile. One should be highly unstable, other should be stable. If it is stable, then only it can react easily. And see, this is unstable, this is stable, then only reacts easily. Both are stable, both are not responding first of all. Both are not responding, no reaction. Both are responding very fastly. So they will fight with each other, they won't compromise. They will fight with each other. So they will fight with each other, they won't combine together due to instability. Instability, no reaction. More stability, no reaction. One should be stable, other should be unstable. That's why two types of cations we are going to generate. So don't confuse here. Stability is different, participating in reaction is different. Depends on reaction, depends on migrating group, depends on the intermediate. We need to use this attack. Here benzene, and here also I am using benzene having a methoxy group. Photochemically, what is the answer? Photochemical, what is the answer? So this is also same, but here now it is lumiketone, dinone. Dinone I given. So see, this is dinone. Here right side one double bond, left side one double bond is there. So on that time, what is your answer? When dinones are given, aromatic ring formation takes place or not? This is phenol. Now two products are expected. So now this is meta as it is. What is one more? Para. One more is what? Ortho. But para is major, only major I am writing. You write two products, say this is major. Now see, this carbon migrates from here to here. See, this point is belongs to this point. Now this is a migrating group. This is not migrating group, this phenyl is a migrating group. This carbon comes from here to here. Now this phenyl is as it is. Over here, out of two phenyl, one phenyl migrates from this position to here. So that position comes here. Now this carbon is this one. Yesterday I explained with mechanism. And see, which is migrating group? Which is migrating group? Phenyl is migrating or para-cyanobenzene is migrating? Phenyl is migrating group. Because para-cyano create unstable cation that can attain aromaticity very fastly. So whichever group is migrating, that group will settle down at either para position or ortho position. Now where it is settled? See here, which group is present? Phenyl. Is it phenyl is migrating group or cyanobenzene is migrating group? Phenyl. Don't think, sir, here cyano is there, it is migrating from here to here. Generally you will think that para position having para-cyano. Now this group is migrating from here to here. That's why you will get this. Generally you will think like that. But that is not true. This is not a migrating group. Whichever group present on para position, that is a migrating group. Whichever is present on meta, that is not a migrating group. From there it is initiated and that will make its termination at either ortho position or para position. So which is migrating group between these two? Which will give unstable cation? This one. Which between these two, which will carry more electrons? Benzene. Now benzene is a migrating group. Whichever is a migrating group, that will settle down on para position or ortho position. Two possibilities are expected. Clear? You write two products, ortho product and para. I am writing para as major, every time you write down para. C. Here I am writing benzene and here I am writing methoxy. So photochemically, what is your answer? Here pH and this is CH3. Photochemically, what is the answer? Dinone phenol rearrangement. Looks like dinone phenol, but that is completely acid medium reaction. Right now we are discussing photochemical reaction. So which is migrating group here? Which is migrating group? Para methoxy is a migrating group. So that you need to write down 3 membered. Clear? This product is different, this product is different. It is a dinone and it is a simple cyclohexene one. Now, which is migrating group here? Whichever carry more electron density, that is a migrating group. So, is it para-methoxybenzene is migrating group? Now this is a migrating group. Whichever group is migrating, that will settle down on para position. So now see, this position belongs to this one. That labeled carbon they will give in exam. Now in this one, which is migrating group? Phenyl is migrating group. Phenyl migrates at para position, methyl present over here. Right? When phenyl migrate, you will get unstable cation. Simply one point you remember. Whichever group carry more electron density, that is a migrating group. Okay, only one point. See, between these two, methox is a mesomeric group. It will give more electron density. Whichever ring carry more electron density, that is migrating group. Now here two phenyls, here see, this carry more electron density, that's why it is migrating from this position to here. So every time remember, this position you need to circle like this. From here group migrating, and that will settle down on para, and one more is ortho. Two products are expected. So this reaction is important. Applications are important. So if you understood clearly, you can give the answer for this. This is double bond O, and here molecule is present. So what is the answer? Cyclohexadienone. I given photochemically. What is the answer? So whichever is more electron rich, that is migrating group. Now in this one, see, is this carbon goes to meta position? First write down meta, write down phenol. Now this position already, this carbon is this one. So here carry 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, this will attach here. So this carbon belongs to this one. Now break this, one of the substitution attaches to para. So this side one product, this side one product. Para is major, that's why I am writing only para. So this is photochemically on irradiation. Xylene. So your answer is this one. It is almost all equal to photochemical product. So this is photochemically activated. This is C double bond O. I am using xylene as a triplet sensitizer. Now it is get activated. So this is get activated. Now state is N2 pi star triplet, because it is a triplet sensitizer. Then what happens? See, break this bond, break this bond. Then here you may expect a double bond, and this is clockwise, and here also it is clockwise, and here ring will be there. So then this will be broken up. Now here double bond, and here it is one more clockwise electron, and here one more clockwise electron. Okay, then go for demotion of electron. This is electron is demoted from here to here. So when electron is demoted, here there is a formation of negative charge, and what about charge here? Positive. Here one of the electron is here. That electron migrate from here to here. Now this hydrogen loses proton to attain aromaticity. Now driving force is attaining aromaticity. So this is OH and this is isopropane. That is the answer. If this molecule is appeared anywhere, remember it is most important molecule, repeated many times. They will give triplet sensitizer and photochemical symbol they will give alpha gamma beta unsaturated adjacent if any ring is present. Your answer is phenol. This position as it is, this position as it is, this particular carbon converts into alcohol. This is given in exam. Even this is also given in exam. So this electron migrates from here to here. That is demotion. So this is, if 2 comma 2 is present, you will get only one answer in presence of xylene. So this is the answer. Open the product, ring chain product is up expected. So when saturation present on second carbon, see if the 2 phenyls presented para, you will get phenol. But when 2 phenyls present on ortho, then what happens, see you will get ring opening product. Total number of carbons are this. See, this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Open from this side. If you open here, put double bond, then C double bond OH. Break here, and you will get the answer. So that is photochemistry of conjugated carbonyls. Next, photochemistry of olefin. Alkene photochemistry. Photochemistry of carbonyl compound is over. Next is double bond photochemistry. Or photochemistry of olefin. So here see, most of the olefins reaction exit state is pi to pi star singlet. Singlet is a real exit state. Especially this molecule is inefficient ISC system. It is inefficient ISC system, unable to generate pi to pi star triplet. So these molecules are unable to generate pi to pi star triplet itself. Itself it is not possible to generate. Inefficient ISC systems unable to generate pi to pi star triplet. Okay. So if I take any triplet sensitizers generates pi to pi star triplet. So these molecules can have a tendency to generate a triplet state by using a triplet sensitizer. So here we can use benzene as a triplet sensitizer, toluene, and even I can use xylene. These are the variable triplet sensitizers for olefin. When olefin is given, if any aromatic rings are given, they are triplet sensitizers for olefin. So on that time, pi to pi star triplet they will be generated. So pi to pi star singlet reactions are different, triplet reactions are different. But this molecule never generate triplet, but they can generate it by using triplet sensitizer. Okay, only one type of reactions are well known, singlet. Suppose if you want to do any triplet reaction done by using sensitizer. If there is no sensitizer is given, on that time go for singlet reactions only. Clear? Now, reactions involved in this one. Double bond can undergo cis and isomerization. Next, this is simple photocyclodimerization. Next, photocycloaddition. Then followed by simple addition. Simple addition is also possible. Total 5 types of reactions are known for olefin. Then intramolecular cross addition. Total 5 types of reactions are known for olefin. Cis trans isomerism, this is important. Mostly it is asked. Then later on intramolecular. Only these two are important. Most important is cis trans isomerization, photocyclodimerization, photocycloaddition. Then this is simple addition, then followed by intramolecular cross addition. Benzene, toluene, xylene are the common triplet sensitizers. Most important questions are coming from cis trans isomerization only. Olefin cis trans isomerism. Cis trans isomerization. Next is cis trans isomerism or cis trans isomerization. Photocyclodimerization approximately equal to alpha comma beta. Photocycloaddition, simple addition, cross addition. See, normally if I take any aromatic ring, this is a stilbene, trans stilbene. Trans stilbene I want to convert into cis stilbene. Two specific methods are available, thermal and photochemical. Thermal, if you want to convert any cis or trans, okay, it is impossible to convert thermally a simple olefin into cis trans isomers. Thermally impossible to convert simple olefin trans isomer to cis isomer. It is possible to convert only under photochemical. See, photochemically it is possible to convert cis isomer. So cis isomer converted to trans, trans can be converted to cis under thermal. So ground state cis trans isomerism not exist. What is thermal reactions? Ground state reactions. What is photochemical reactions? Excited reactions. So under thermal conditions it is a ground state. At ground state cis-trans isomers not exist. We can't convert cis to trans under thermal. Photochemically we can convert cis isomer into trans and trans isomer into cis. That's why interconversion of cis-trans possible under photochemically but not under thermally. Ground state we can't convert trans to cis, cis to trans, but photochemically we can convert. This is very important point it is. Thermally it is impossible, photochemically it is possible. See, at ground state or thermally cis-trans isomerization. Cis-trans isomerization does not exist. It is impossible to convert at ground state. Ground state or thermal. Ground state thermal not possible. So now it is possible at excited state or not? At excited state or photochemically, cis-trans isomerization is exist. Photochemically possible but thermally not possible. This point is very important for next topic. Upcoming one more topic is there. There I will ask this question. Cis-trans isomerism for simple olefin possible under photochemical, not under thermal. Thermally not possible, photochemically it is possible. So, in presence of light, if I take any cis-trans isomers, in presence of light, cis-trans isomers develops, what they develops? Photostationary state. Photostationary state. This point is important one, you remember this. What is a photostationary state? When light is irradiate on any cis or trans isomer, it may be cis isomer or trans isomer, when light is irradiated on any one of these, on that time they will develop a photostationary state. This point is very important. Photostationary state. In presence of light, cis-trans isomers develops a photostationary state. So what is photostationary state? See, the constant composition of reaction mixture or cis-trans isomers in photochemical reactions. In photochemical reactions, constant composition is observed, that is known as photostationary state. Photostationary state is a state where constant composition of reaction mixture is observed. Reaction mixture nothing but either cis and trans or cis. The constant composition of reaction mixture under photochemical reaction is known as photostationary state. Means always cis trans having a constant composition. Here only that word is important, photostationary state. Right, see this. Here I am writing a cis isomer. cis isomer responsible to give a trans isomer under photochemically. Okay, so here I am writing 330 nanometers of wavelength I am using and I am irradiating. On that time see, 95% of cis isomer, 5% of trans isomer is appeared. Or 93.7, otherwise you can take better. Real composition is 93 and this is 7%. Here cis is 93, not trans. Okay, be careful. This question given in DL exam, recently DL exam conducted by Telangana state. Okay, so on that time this question is given. Most of the people they think trans is 93%, that is wrong. When they given light, what is the light wavelength? 313 nanometers. So what is the wavelength of absorption wavelength of this one? 295 nanometers of wavelength. 295, this is 295. 295 absorption wavelength is required for trans. But for cis how much? 280 nanometers of absorption wavelength is required. This is absorption wavelength of this one. It is absorption wavelength of trans steel beam. This is absorption wavelength. That how much radiation I am using? 313. So when I use 313 nanometers, whichever isomer having a very closer lambda to this wavelength, only that will absorb the energy and that will convert it to opposite isomer. That's why whose percentage decreases. See, this 313 is very close to either trans or cis isomer. This 313 is very closer to trans. So that's why trans will absorb that energy. That energy transfer to this one. Okay, and this trans isomer starts converting into cis isomer. That's why this population decreases. This population is very high because, why this population is very high? Because it is not absorbing this wavelength. So percentage of products at photostationary state, when you apply 313 nanometers, always this is constant, it is also constant. That is called photostationary state. The state at which there is a constant composition of reaction mixture, that is called photostationary state. At 313 nanometers, these two maintain constant composition. Suppose if I change the wavelength, they will also change. Clear? So always reaction products of cis and trans depends upon the irradiate wavelength. If irradiate wavelength is changes, this percentage also changes. This irradiate wavelength, whichever is very closer, so that particular stereoisomer will absorb that energy, convert it to opposite isomer. So that's why trans isomer is converted to cis isomer. That's why this population is very less. That is called photostationary state. Photostationary state, remember only one point. First you remember, ask them what is the wavelength. So this wavelength will decide these percentages. This percentages is always constant if you maintain this wavelength. Clear? Suppose see, if I take any 1 gram, it is 1 gram. It is also 1 gram. Both are at equilibrium. If I apply 330 nanometers, then this is 7% and this is 93%. Clear? That is called photostationary state. It is a constant reaction mixture state by applying a constant wavelength. Until and unless wavelength is changes, this percentage remains constant. If wavelength changes, this percentage changes. So that's why cis trans isomers percentage at equilibrium depends upon wavelength. So one more question I will give. Suppose if I give 280 nanometers here, 280. If I give 280, that wavelength matches to which one? Cis isomer. Then cis isomer percentage transfer to trans. On that time trans population is very high, cis will be very less. Until and unless if you change the wavelength, that percentage never changes. That is always constant. That constant percentage nothing but photostationary state. If wavelength is constant, percentage of cis and trans isomers at equilibrium also constant. That is the statement. Only that point if you remember, you can attempt the question. This is possible if you maintain suitable light. Suppose if thermal if I use, not possible. We can't convert this to. What is photostationary state? It is a state where two stereoisomers having a constant composition with a suitable wavelength. It is a constant composition of reaction mixture in photochemical reactions. In photochemical reactions, it is a constant composition always. Suppose if you take 100 grams, even if you take 50 grams, even if you take 1 gram, what it may be, percentage is always 7 and 93 only. Irrespective of the amount. Initially Cis is how much? 0. Here it is 100. Suppose see, I am taking 100 grams. 100 grams of which one? 100 grams of this I am taking. Here initially 0 gram. I applied 330 into trans isomer. Then trans become how much? 7% and this is 93. Is there any Cis is there initially? Initially Cis is there? No. I taken what? 100 grams. 100 grams of trans I taken, I irradiated with this wavelength and it is converted to this. Clear? So that is called constant composition. So that's why this question is most important. Generally, wavelength, whichever wavelength is given, that wavelength is closer to whichever the stereoisomer, only that isomer starts converted to opposite isomer. That population decreases. So percentage of these two isomer depends on which one? Percentage of cis and trans isomers depends on irradiate wavelength. So the applied wavelength very closer to whichever the isomer, that isomer percentage decreases, that amount will be transferred to opposite isomer interconversion. Here who is converting? Cis is converting to trans or trans converting to cis? Trans converting to cis. Is it cis converted to trans in this one? No. Cis is not converted to trans. Why? Because this wavelength is matches to which one? Trans. Suppose if you decrease wavelength and if it is very close to this one, then cis converted to trans. So they can be interconvertible by maintaining a suitable wavelength. That's why I am saying light. In presence of light we can convert cis to trans, trans to cis. But suitable wavelength is required. All wavelength it is impossible to convert these two. Only suitable wavelength. There is cis to trans or trans to cis. That is called photostationary state. Clear? Right. Clear? Okay, right. Percentage of cis-trans isomers depends on, where it is depends? Percentage of cis-trans isomers depends on irradiate wavelength. Irradiate wavelength. Percentage of cis-trans isomers depends on irradiate wavelength. Okay, see. The absorption wavelength closer to, the absorption wavelength closer to cis or trans isomer absorbs energy and interconverts to opposite isomer and interconverts to opposite isomer. The absorption lambda closer to either cis or trans isomer, any one. Okay, that will absorbs energy and interconverts to opposite isomer. So here example, in still bin 313 nanometers, very close to, here right, in cis-trans still bin 313 nanometers, very close to absorption wavelength of, or absorption lambda of, which one? Absorption lambda of trans isomer. Okay, therefore trans still bin converts into, trans still bin converts into which still bin? Cis still bin at 313 nanometers. So this point is important. Clearly I am giving. The statements they are asking, question in the form of statement they are asking. So can you convert cis-trans isomers under photochemically? They will ask. Possible or not? Yes, it is possible. Is it cis-trans interconversion depends on wavelength? Yes. At all wavelength can you convert cis-trans isomers? No. Only with a specific wavelength, either cis isomer, either trans isomer will absorb that energy and that will be interconverted. So percentage of cis-trans depends on which one? Irradiate wavelength. So that is called constant composition. At this particular wavelength they will maintain this percentage only every time, irrespective of the amount. You may take 100 grams, 200 grams, 300 grams or 1000 grams, what it may be. Always it is 7%, always it is 93%. It is not about stability. See, it is not about stability. This is more stable as compared to this one. This is not stability percentage. Generally whenever in exam if they given 93%, you will think about trans. That is wrong. In photochemistry, percentage if they given, that is after absorbing wavelength. Between these two, which is more stable? Trans is stable as compared to cis. But this is after absorbing energy, how it is interconverting. So after absorbing, trans taking energy and activated, convert into cis. So at this particular wavelength, these two always maintain a constant percentage. That constant percentage known as a photostationary state. The state at which two stereoisomers will maintain a constant composition by absorbing suitable irradiate wavelength. That is called photostationary state. So here I am writing this. Is it possible to irradiate with light? Yes. Write down corresponding opposite isomer. Cis-trans here this is CS3. Write down corresponding isomer. Here wavelength is not mentioned. If wavelength is not mentioned, what it means? So what is the meaning if they not mention wavelength? See, in this molecule 2 phenyls I can write trans, now I am writing cis. Then this methyl is possible. Means see, I take a wavelength, any wavelength, one particular range, any wavelength, take any wavelength. Can you convert trans to cis? Any wavelength, possible or not? Any wavelength in a particular range, at one particular wavelength, can you convert trans to cis? Any wavelength, can you convert cis to trans? All wavelength are not using. I am not using. See, what is light indicates? HV indicates what is the wavelength? Suitable wavelength. So in a particular distance, many wavelengths are there. With a suitable light irradiation, I can convert like this. That is the meaning. But real wavelength if they given, it is suitable only for one stereoisomer. So here light is given. Light in one particular wavelength suitable for this one. Light in one particular wavelength suitable for this one. So we can convert left to right, right to left. If wavelength is not mentioned, both can be interconvertible. Both are possible to convert with a suitable absorbed wavelength. Clear? Will you write this? Here writing reactions are very easy, but if they ask clear question, not easy to understand. That's why I'm saying key point is photostationary state. What is photostationary state? Why trans percentage is less as compared to cis percentage if I irradiate with 330 nanometers. So still bin values are given because still bin value given in exam. Only still bin value is fixed. So it is remembering each and every isomer value is not easy. At least one molecule remember. Still bin regularly they are asking. 330 nanometers suitable for which one? 330 nanometers suitable for which still bin? Trans still bin. Is it trans converted to cis on the time or cis converted to trans? Trans converted to cis. So write corresponding opposite isomer, cis isomer. You write carboxylic acid above, write 2 methyls opposite side. So you write this methyl below direction, trans you will get. Wavelength is not required. We can convert them. Now see this is it cis or trans double bond? Is it cis or trans double bond? Cis double bond. Cis double bond, now it is converting like this. Here, is it trans or not? Is it a trans? Now here total how many carbons are there in this one? 8 carbons. 8 or 6? 8. Now see I am writing 1, 2, here 1, 2. What is this? Cis isomer. What is this? I think you observed this somewhere. By watching this one chapter you need to recollect. Stereochemistry, where I explain. Chiral axis or chiral plane? Chiral plane. Is it optically active? No. But what is this? Optically active. Photochemically, an inactive molecule you can convert into active molecule. That is the specialty of this concept. Trans-cyclooctane. Trans-cyclooctane. This is called cis-cyclooctane. Cis-cyclooctane can be converted to trans-cyclooctane. Is it cis converted to trans? Yes, with a suitable wavelength. Now initially it is a achirol. This molecule is achirol and this is chirol. Optically active. So this is optically active due to what is the reason? Chiral plane. Questions they will frame in a different ways. Concept remains same. Way of framing question is different. So that's why you should be strong in concept. Optical inactive cis isomer converted to optical active trans isomer under photochemically. See, one inactive molecule by absorbing energy converting into optical active molecule. So we can prepare chirality under photochemical? Yes. chirality can be created under photochemical. Like that statement they will give. So examiner keep this molecule in their mind and they will frame questions with options. So be careful with this. See, cysteines isomerization. Cysteines isomerization is singlet and triplet reaction. So this reaction possible at singlet as well as triplet state. This are also asked question in exam. Cysteines isomerism possible under singlet state or triplet state they will ask. Pi to pi star singlet possible, and even by using a triplet sensitizer this reaction possible. See here I can use direct light, even I can use triplet sensitizer, your answer remains same. Singlet and triplet answer same. Clear? Singlet interconversion cysteines possible. Triplet interconversion cysteines also possible. So in exam they will ask cysteines interconversion or cysteines isomerism possible only pi to pi star singlet state. Cysteines interconversion possible pi to pi star triplet state. Both they will give. Which is right? Both. That's why these kind of points are very important. You need to know which state it is possible. Some reactions possible only singlet, some possible only triplet, some possible both states. Is it singlet state reaction or triplet state reaction? Both. Cysteines interconversion possible under singlet as well as triplet state. Both are possible. Okay, so first one see, I will show. Pi to pi star singlet, cysteines isomerization. Pi to pi star singlet, cysteines isomerization. Pi to pi star singlet, cysteines isomerization. See this. First what I am taking? I am taking a cis olefin. How cis olefin looks? R, hydrogen R, right? What is the state of this olefin? S0 or not? This is S0. So next I am writing a trans olefin. Don't write, just listen first. Here it is a trans olefin. How to write trans olefin? R above, R below, right? Now this is on photochemical irradiation. It is a direct process. So what is direct? Cis to cis only, cis olefin. Now here what will get? This is cis and here also cis. So what is the state? What is the state of this one? S1. This is S0 and what is this? S1. This is called, remember this word, vertical singlet excited state. You remember that word, in write later. Vertical singlet excited state. It is having a same stereochemistry what maintained by ground state molecule. Excited cis isomer, ground state cis isomer having a same stereochemistry. Memory retains. They retains their memory. So what is VSES? Vertical singlet excited state. Next followed by C, same photochemical direct irradiation. Now I got trans olefin. How to write trans olefin? This is R above, R below, here H and here H. So this is one. So this is vertical singlet excited state. What about this state? Is it S1 or not? Clear? First I taken cis isomer. Direct irradiation, I got singlet state. VSES nothing but vertical singlet excited state. When any cis isomer or trans isomer, after absorbing a suitable wavelength, it will be excited, and that will reach us to singlet state. When they reach us to singlet state, they can remember their ground state memory. What is the meaning of ground state memory? What is the meaning of ground state memory? See, when you came from a poor family, after reaching a high standard, if you remember your poor standard in your mind, that is called you are retaining your memory. You are recollecting your memory. That is this state. After reaching excited corresponding state, this molecule retaining their memory. They have memory. They know from where it will came. It is arrived over here, and they know what is the stage of this particular molecule initially. Means cis to cis, they have that memory. I came from cis. They are saying that initially I am a cis, still I am cis only. They have a memory. Now what happens, see here. This is undergo relaxed by 90 degree CC twist or 90 degree CC rotation. After reaching S1 state, so this carbon undergo rotation. When this carbon undergo rotation, then what happens, see, this is carbon-carbon double bond, and see, this is above and this is below. This is R and this is H. Okay, remember this state, this is a temporary state. It is a temporary state. See, what is the angle between these two? 0 degree. Two methyls are same side or not? 0 degree. What about these two? 180, opposite. But what about this alkyl? They are maintained by how much angle? 90 degree. So alkyl is here, other alkyl here. One alkyl is right side, other alkyl is above. What about here? Two methyls are how they are present initially. Two methyls are cis, same side. Now in this case, two methyls are opposite side. But in this one methyl right side, other methyl above. What is the angle between these two? 90. So this particular molecule reaches to this state, and this I am going to write like this. This is R, carbon-carbon double bond, and this is H. This is R, and here it is H. So this is called non-vertical singlet excited state. Memory lost state. Stereochemist inverted. They lose memory completely. They don't know from where it came. Memory lost state. They don't know. They don't know whether came from cis or trans. It is same way, this is undergo CC rotation. Same point you need to relate here. See, relaxed by 90 degree CC twist or rotation. So after CC twist or rotation, both, if it is come from cis or it maybe comes from trans, both will reach us to constant state. Both will lose their memory. So if any stereoisomer, either cis isomer or trans isomer, after losing their memory, they don't know whether came from cis, they don't know whether they came from trans. So it is a constant losing memory state for both cis isomer and trans isomer. That state is called non-vertical singlet excited state. Memory loss state. They know from where it came. They know from where it came. This is came from? You came from? Where you came? From your respective village. Right or not? First you will say your village name. Suppose if you went to other country, then you will say you came from your India. You will came from India. Right or not? Means you are not losing your memory. Until and unless if you are not losing your memory, your state is singlet state only. So after 10 years, 15 years, 20 years, 25 years or 50, 60 years, one particular stage, you lose your memory. You don't know from where you came. That is this state. Right or not? Your granddaughter or your grandchildren will ask you, do you know where you remember? Do you know from where you came? So on that time, this is your situation. You are thinking, So from where you are coming? You forget your village name, your district name, and your country name. Finally, wherever you are settled, even that name is partially, temporarily, that name is fixed. This stage will be common for both cis isomer and trans. Cis isomer I used vertical singlet exit, rotate and give this one. This will generate singlet and that will generate this one. Now see, from here onwards, equal partition. Okay, so here it is, relaxed and partitioned. So here also same, relaxed and partitioned. So on that time see, see what is this isomer? This isomer is cis. What is this isomer? Trans isomer. Initially I started with which one? Initially I started with cis, vertical singlet exit state, then non-vertical. This is memory loss state. Then finally I got, now my question is it cis is giving trans? Memory loss first of all, you are unable to say. You are unable to say whether this, see, what is it is a common state for both cis and trans or not? Cis and trans it is common state, then giving this one. Then see, trans comes from, trans to trans possible? Commonly we can't say trans to trans, right or not? So we can say that this is responsible to give trans, and even if you start with a trans responsible to give cis with a constant intermediate, that is called non-vertical singlet state. So this is a constant for these two. It is a constant intermediate for cis isomer and trans isomer. After getting constant intermediate, they lose their memory, then they are distributed equally. Equally means based on absorption wavelength. It is always 7%, always 93%, 93 or 7. Even if you take 7 grams, 7 grams I taken. I prepared the 7 grams. In that 7 grams, 93%, 7%. Try to understand. Okay, I taken 100 grams, initially 100 grams. 100 grams of only cis is there, any trans? No. Suppose if I take 100 grams of trans, now I got this one. Then after reaching this state, it is giving 93%, it is giving 7 grams. 93 grams, 7. Initially any cis is there? Any cis is there? No. So in order to convert cis and trans, you can use either cis isomer or trans isomer. But cis isomer first converted to this, even trans isomer also converted this, and finally you will get these two. And composition is not fixed every time. That depends on irradiate wavelength, this wavelength. Right. Non-vertical singlet exit state. This is called vertical singlet excited state. You can start with cis isomer or trans isomer. that is also called intermediate state. Non-vertical singlet excited state is a common state for both cis and trans isomer. So now these two alkyls are separated by an angle of how much? 90 degree. 90 degree separation, these two. So can you start with cis? Can you start with cis? Yes, you can start with cis, but minimum 1% is, some amount is required if you want to start with cis. Suppose if it is 0, can you start with suitable wavelength? Wavelength is suitable, but 0%, possible? See, for this cis, I given a suitable wavelength only, but cis is not there, possible? No. First of all, person should appear, then only it will observe. Right or not? But here composition of liberation is remain same. Suppose if it is a 1 gram, suitable wavelength of cis reaches to intermediate. This is intermediate. From there onwards, percentage remains same. 93%. 93%, what is this? 7%. Still been I am saying. Initially, how many grams are taken this one? Initially, how many grams? 1 gram. 1 gram suitable wavelength, then percentage changes. Here see, 1 gram, what is the wavelength? 313. On the time, percentage 93, 7%. If I take 313 nanometers, here suppose if 1 gram is there, this 1 gram absorb this 313 and it will give, this is 93, this is 1. Suppose if I give 1 gram, if I take 313, is it possible to give? This isomer is a cis isomer whose wavelength is 280 nanometer. 280 nanometer. I am supplying 313. Is it possible to observe? Yes, remember, it is possible to observe because in this one there is no trans right now. Now it is absorbing 280, 313, very close to 280 or not. Suppose if 295 is there, it won't absorb. So this is 0, this is 1 gram. See, this 1 gram absorbing 313. Total 1 gram cannot absorb at a time. In that, whichever molecule absorbs 280, they will convert it to this one. Then, after reaching this, trans is what? Trans is 7%, cis is 93%. Once trans is reaches, trans percentage is converted to cis. Try to understand simple point. Even if it is 1 gram, possible to absorb 313, but initially there is no trans isomer. But when 313 irradiated on 1 gram, in that see, in this 1 gram, 0.1 gram converted to what? Trans. How much grams is left here? 0.9. Once if it is reaches to trans, this trans never allow this 313 to this 1 gram. How much amount is converted here? 0.1 to which one? See, in that one 1 gram is there or not? 1 gram, I am using 313 nanometers. If trans is not there, this 313 can irradiate on cis. In that, some amount will be converted to trans. Start converting. All cannot convert at a time. This 1 gram, 0.1 gram converted to which isomer? Trans. This trans, it will take this energy converted to cis. Because trans having more absorption as compared to cis with this wavelength. If trans is not there, then only cis can absorb. When cis starts converting into trans, if cis starts converting into trans, this wavelength absorbed by trans starts converting into cis. Then automatically which percent is decreasing? Trans percentage decrease. This is cis isomer, it is a trans isomer. Okay? See, there is no trans initially. Now I am applying 313. Suppose if trans is present, this 313 suitable for which one? Trans is there, it is suitable for trans only. But if trans is not there, then only one. So this will be converted here. Initially here 1 gram is there. Now cis starts converting into trans. Cis starts converting into trans, how many grams? 0.1. Now here how many grams are left? 0.9 grams are left. When cis 0.1 gram start converting into trans, this trans never allow this 330 nanometers to convert remaining amount to trans. It will absorb this one and starts converting into cis. I think you followed. Or sorry, explaining something, but is blinking in your mind like that. I think so. Followed? This wavelength is suitable only when if corresponding partner is not available. Once if corresponding partner start generating, this partner never allow this wavelength to take this partner. It will accept this wavelength and starts converting into cis. So on the time trans percentage decreases or increases? This molecule want to give trans, but trans starts converting into cis, means this percentage decreases, this percentage increases. That's why cis is high, trans is low. That's why this is common state. Clear? So see this. This is cis isomer, and here I am writing a trans isomer over here. Now this is photochemically irradiated cis isomer, and here also photochemically irradiated. Now this will reaches to vertical singlet excited state, and here also reaches to vertical singlet excited state. This is little bit lower as compared to this one. This is for cis isomer, And what about this? This is for trans isomer. Now both will reaches to. Now this both will reaches to one state. What is that? Non-vertical singlet exit state. Now from there onwards you will get cis isomer and here trans isomer. First cis isomer absorbs energy excited. Trans isomer also absorbs energy excited. Both having a constant energy. What is that? Non-vertical singlet exit. From there onwards percentage will be distributed. So this is called non-vertical singlet excited state. It is cis isomer high energy, it is low energy. It may be high energy or low energy. Once if they reaches to non-vertical, based on absorption wavelength, distribution is remain same. So it is absorption wavelength of cis olefin, absorption wavelength of trans olefin. They will reaches to corresponding states. Once if they reaches to corresponding states, they come back to non-vertical. Non-vertical energy always less than vertical energy. After reaching non-vertical, percentage of contribution remains same. That is called photostationary state. So you write second one, it is almost all same, but only thing is I am taking a triplet, pi to pi star triplet, cis trans isomerization. First I am taking cis, here also first I am taking cis, here I am using a triplet sensitizer. Once if you take triplet sensitizer, what is your answer? T1. So triplet vertical triplet excited state. Here also same. Vertical triplet excited state. This is T1. Here T1 and here also T1. Now here same memory loss state. It is non-vertical triplet excited state. Only singlet replaced by triplet. Your answer remains same. Here also cis isomer and trans isomer. You can proceed reaction with triplet and singlet. Ground state, triplet sensitizer reaches to T1. Here also reaches to T1. Now cis converted to non-vertical triplet excited state. Memory loss state. Same points as this. Then after this, relaxed and partitioned to cis isomer, trans isomer. This is always constant. You can take with cis isomer, you can take with trans isomer. You can prepare this composition constantly. That is called photostationary state. Initially this is 1 gram, this is 0. Still we can prepare trans. It is 100 gram, 0. Still we can prepare trans. You can initiate reaction with either cis isomer or trans isomer. Your resultant product percentage is always same. That is called photostationary state. Always maintain constant composition mixture. Photostationary state is nothing but constant composition mixture. Memory loss state. So in place of singlet, write down triplet. Then you write this. Vertical triplet excited state, non-vertical triplet excited state, both are same, and partitions almost all same. What I would like to say is, by replacing singlet state to triplet state, your answer remains same. Indirectly I am saying, both singlet, triplet responsible to give cis trans isomers. vertical triplet excited state.